last lecture, we had started looking at scattering from a crystal of a finite size, and in this we assume this finite size that there is a crystal which have n1 atoms along A axis, n2 atoms along B axis, and n3 atoms along C axis. And the way we visualize this scattering is, let us consider a lattice point at an origin marked as A, and another lattice point at point B, and from the location of the lattice point B is given by the vector r, as one can see from this figure. From here one determines what would be the path difference when the X-rays reach the point Q, and if the path difference is an integral multiple of wavelength, then we will have constructive interference. Based on this, we went further and determined what would be the resultant wave at point Q, which is given by summation over all the r vectors, where the r vector itself is a lattice translation vector UA plus VB plus WC, and we have in this case the scattering centers only at the corners of a primitive unit cell. And then further expanding, one got the resultant wave at point Q written in the form of 3 summations. Then, as we saw in the last class, towards the end of the last lecture, that each of these summations are nothing but a geometric series summed over n1 terms, the second one over n2 terms, and a third one over n3 terms. And these, one used the relationship for the summation of a geometric series, and one got the summation result for the first term, for the second term, and the third term, where note that the psi 1, psi 2, psi 3 are pi upon lambda s dot A, where s is a scattering vector, A is a translation vector in the unit cell. Similarly, pi upon lambda s dot B is psi 2, and psi 3 is pi upon lambda s dot C. Now, we go further with this and write down the resultant amplitude at point Q by multiplying all these 3 summations, and one gets the following result, that the resultant wave at Q can be written as phi naught upon r e to power I omega t, and then one writes down the individual summation of the 3 geometric series. 1 minus e to power I to n1 psi 1 divided by 1 minus e to power I 2 psi 1. This is the first summation. The second summation similarly would be 1 minus e to power I to n2 psi 2 divided by 1 minus e to power I 2 psi 2, multiplying by the third term 1 minus e to power I to n3 psi 3 divided by 1 minus e to power I 2 psi 3. So, this is the resultant of the wave, and just this thing, let me also write down that psi 1 equals pi upon lambda s dot A, psi 2 equals pi upon lambda s dot B, and psi 3 equals pi upon lambda S dot C. Now, what would be the resulting intensity? The resulting intensity, let me call that as I, would be nothing but take the amplitude y multiplied by its complex conjugate y star. Now, what would be the complex conjugate of I star? So, let me just make a brief digression here. That let us consider each of these terms separately, and all of these terms, if you look at the numerator or you look at the denominator, they are of the form 1 minus e to power I x, where if I look at the first term, x is nothing but 2 n1 psi 1, or let me actually not call it e to power I x, let me call this as e to power I 2x. So, x then for the first term in the numerator of the first term would be n1 psi 1, denominator would be simply psi 1. Then for the second term it will be n2 psi 2 in the numerator, and the denominator would simply be x would be simply be psi 2, and you can see that for the third term it will be n3 psi 3 the value of x, and for the denominator it would only be psi 3. So, let us see, if I look at this complex function, its complex conjugate would simply be 1 minus e to power minus I 2x. Now, if I take these two terms, 1 minus e to power 2x, and I multiply it by its complex conjugate 1 minus e to power minus I 2x. So, let us see what do we get. Let us just expand this. So, I will get on expansion, I will simply get 2 minus e to power I 2x plus e to power minus I 2x. Now, one can write the expanded form of e to power I 2x in terms of trigonometric functions as simply cos 2x plus I sin 2x. And similarly, if I write e to power minus I 2x, this would be cos 2x minus I sin 2x. So, if I just substitute this in this equation, I will skip few steps and I will write 2 times 1 minus cos 2x. This cos 2x can be expanded to 1 minus cos square x plus sin square x, and therefore, the product of the complex number with its complex conjugate would become 4 times sin square x. So, now this becomes a simple matter. So, looking at it, let us multiply all this. So, I will get phi 0 upon r, and now e to power I omega t will have to be multiplied by its complex conjugate as well. It will have to be multiplied by it. So, let me actually in fact, let me write down the full complex conjugate, so that things are clear. So, resultant intensity I is equal to y star. So, now let me write the complex conjugate. The complex conjugate would be phi 0 upon r e to power minus I omega t into 1 minus e to power minus I 2 n1 psi 1 divided by 1 minus e to power I 2 psi 1 multiplied by 1 minus e to power minus I 2 n2 psi 2 divided by 1 minus e to power minus I, here also this will be minus I 2 psi 2. Third one, 1 minus e to power minus I 2 n 3 psi 3 divided by 1 minus e to power minus I 2 psi 3. So, therefore, the resulting intensity, which is y star. So, E 1 phi, this will become phi naught square upon r square, e to power minus I omega t multiplied by e to power plus I omega t would simply be unity. So, this term will disappear, and then I will have, let us now multiply individually. So, multiply this term with this term. If we do that, so multiply the numerators and multiply the denominators following this. So, here in the numerator x is simply n1 psi 1. Therefore, I will get 4 sine square n1 psi 1. Denominator would simply be 4 times sine square psi 1. Now, the 4's will get cancelled. Similarly, I can now write the rest, and the second term would become sine square n2 psi 2 divided by sine square psi 2, and the third term would be sine square n3 psi 3 divided by sine square psi 3. So, we want to investigate these individual functions, sine square n1 psi 1 upon sine square n psi 1 and so on. So, if I look at each of these functions separately, let us try to figure out where can I get maximas in this. So, I am not go through that, this is pretty straightforward, but let me just go through a few steps. So, what happens when, let us say, investigating the first term? What happens when psi 1 approaches an integral multiple of pi, where n could be 0, 1, 2, 3. All these three functions are similar. So, if I know what happens when the first one goes like that, the second and third will also be like that. So, I am trying to find out that what would be the value of this function when psi 1 tends to n pi. Now, in order to find this limit, look at a more general function. Let us say that I have a function sine square nx upon sine square x, and what will be its value when the limit for x approaches, let me use some other instead of n, let me call this as h pi, where h is an integer. So, here also let me just call it as h pi. So, what happens here? Let us, in order to solve this, if I directly substitute h pi in this, I will get 0 upon 0, which is an indeterminate quantity. So, let us use what is the well known L'Hopital's rule. So, L'Hopital's rule means that you just differentiate the denominator and the numerator. So, one can then write limit as x tends to h pi, after differentiating I will get 2n sin nx cos nx divided by 2 sin x cos x. This could be written as limit x tends to h pi n sin 2 nx divided by sin 2x. This then becomes, again differentiate. On a second differentiation, I will get two n square cos 2 nx divided by 2 cos 2x. This 2 will get cancelled the way this 2 and this 2 got cancelled here. Now, substitute for x as h pi where h is an integer, then clearly the cosine terms would simply be unity, and hence in the limit this function goes to n square. We can quickly show the plot of this function as well, that how this function behaves. So, if we look at this function sin square nx upon sin square x, and this is plotted for different values of n, and remember this n is nothing but going to be the number of atoms or number of scattering centers. So, for n is equal to 1000, as you can see the function is just about 0 everywhere else except at some specific values. So, at 0 there is a peak, and this is actually pi there is a peak, and so on. At 2 pi also there will be another peak, but between 0 and pi this function is more or less 0. If I change the value of n, I reduce the number of scattering centers, then also the function remains more or less 0 everywhere else except for 0 and pi, but you can see that there is a slight bit of broadening of the peak. If I even reduce it further to n is equal to 10, then you can see a significant broadening of the maxima, and even in this region there will be what are called as subsidiary maxima, but they are still quite small. But this is significant, this broadening of the peak. What it is implying is that if I make the crystal size small, then the peaks are not going to be as sharp, the peaks are going to be broadened. And if the crystal is a large size, which means large number of scattering centers, then one will get very sharp maximas at specific values of psi 1, psi 2, psi 3. So, therefore, if I have to now get the maxima, so I can then say that I, the intensity goes to I max when psi 1 equals h pi, psi 2 equals k pi, and psi 3 equals n pi. All the three conditions have to be met to get a maxima, because you can see from such functions that the way the function behaves, even if one of the sine terms, the sine square nx upon sine square x term, that function goes to 0 more or less. If this condition is not satisfied, the entire intensity will go to 0. So, therefore, there is a specific condition for diffraction to occur or for scattering to have a finite intensity, and that, so I can further write this expression as we know that what is psi 1, psi 2, psi 3. So, I can now substitute for psi 1, psi 2, psi 3 and write down, where I should say that h, k and l are integers. So, if I just go back to this, the maximum of this function will correspond to n1 square, maximum for this function will correspond to n2 square, maximum for this function will correspond to n3 square. Hence, I can write I max as phi 0 square upon r square n 1 square n 2 square n 3 square, and this happens when these conditions are satisfied. And just before I continue this peak broadening, you may have known about this, that there would be a widening of the peak for when the crystals are of very small size. So, small crystallite size will produce peak broadening, that just comes out of this analysis. So, let me write these conditions now in a different way. So, we know that psi 1 equals pi upon lambda times the dot product between the scattering vector S and the unit cell vector A, and this would be equal to h pi. Psi 2 would be pi upon lambda S dot B, and this is equal to k pi, and psi 3 equals pi upon lambda S dot C, which is equal to L pi. Now, these are what we call as the Laue conditions. And I can sort of slightly modify these. So, after all, I can write this pi's I can cancel out, and I can write these conditions as S dot A equals h lambda, S dot B equals k lambda, S dot C equals L lambda. Now, let us try and understand how can I interpret this Laue condition. So, in fact, I will now give a geometric interpretation of the Laue conditions. Let us first consider the scattering vector S. We had a geometric interpretation for the scattering vector S in terms of the incident vector and the reflection vector or the scattering vector small s. So, I had this is my incident beam vector, unit vector, this is my scattered beam unit vector, and S, which is equal to S minus S naught, would be simply be, if you think about it, would be this vector, the scattering vector. So, S is the scattering vector. Or I can simply bisect the angle between the S naught and the S unit vectors, and my scattering vector S is nothing but a vector which is perpendicular to this imaginary plane, which let me call it as an imaginary reflecting plane. So, as if I have an incident beam which hits this imaginary plane and gets reflected. So, I have an incident beam at an angle theta and I have got a reflected beam at an angle theta. Now, since S and S naught are unit vectors, the magnitude of the scattering vector S would be nothing but 2 sin theta. Now, let us try to put the scattering vector capital S in crystal coordinates. So, we can rewrite the Laue conditions in crystal space. In crystal space, I have my A vector my B vector and C vector, and I have the scattering vector S out here. Let the scattering vector S make an angle of alpha with the A axis, make an angle of beta with the B axis, and make an angle of gamma with the C axis. Then let us write these conditions in slightly different way. S dot A now can be written as the magnitude of S multiplied by the magnitude of the unit cell vector A times cos alpha, and that would give me S we know is 2 sin theta. So, I can write it as 2A sin theta cos alpha. Similarly, S dot B would be 2B sin theta cos beta, and S dot C would be 2C sin theta cos gamma, and each of these terms would be equal to H lambda equals K lambda equals L lambda. Now, let me draw one more little bit more. We had said that this scattering vector S is perpendicular to this imaginary reflecting plane. Let me draw that plane as well in crystal space. So, let us say that this is the plane to which the S vector, the scattering vector, is perpendicular. So, and let us say that now we are drawing in crystal space, so I can always define this plane as some with Miller indices HKL, that this plane in crystal space can be defined as with Miller indices HKL, which means that it will intersect the A axis at A by H, it will intersect the B axis B by K, and it will intersect the C axis at C by L. One can also see clearly from this diagram that if I have to find out what is the interplanar spacing D for this HKL plane, it can be defined in terms of the orientation of the S vector in terms of their angles alpha, beta, gamma with the A, B and C axis. So, in fact, one can easily write that the interplanar spacing this interplanar spacing we had covered early on in the lecture. So, if there is some confusion, one can go back to that video to look at the explanation for the interplanar spacing. So, the interplanar spacing D can be written as from this diagram as A by H cos alpha, or it can be written as B by K cos beta, or C by L cos gamma. Now, let us substitute this interplanar spacing into these equations. So, on substitution, because I have clearly you can see I can bring H on the left hand side or K on the left hand side or L on the left hand side, and I will have A by H cos alpha, B by K cos beta, C by L cos gamma, and on substitution we simply get 2D sin theta is equal to lambda. So, we come to the well known Bragg equation which we had derived earlier. And if this plane HKL had a common factor n, then the reflection condition can be viewed as either a nth order reflection from the plane h upon n, k upon n or L upon n indices, or it can be a first order reflection from the plane HKL. So, essentially we arrive at this Bragg equation, which is looking at only the first order reflection from planes H, K and L. So, in this lecture one has seen the relationship between now the Laue diffraction conditions to the Bragg diffraction condition, and we basically find that the two approaches converge to the same point. With this I conclude this lecture. Thank you.